Today, I'd like to show this title, and I'm so honored to be here and happy to present our recent research results and my appreciation to the Professor Hirzinger. And this is outline. Remote brain for whole body behaviors. I presented at ISRR 6 with a videotape. The Professor Hirzinger encouraged me by requesting the video. He's the first person I handed the videotape. And the second topic is inherited and shared mother environment. It's still working in our lab at the bottom layer. And the third is future challenges for body, brain, and users. Ongoing recent topics I will show. And this is the rough history of our lab, JSK lab, Jouhou System Kogak Robotics lab. Professor Inoue started that 1977, and I joined 1981 as a master course student. And today's talk, my talk is remote brain robotics, started from here, 1992. So the first topics is the remote brain for whole body behaviors from 1992. My first work was the hand-eye system, the rope handling, which is presented at the first ISRR. And at that time, I used a single camera with a stereo mirror, 4-mirrored adapter to generate motion plans. After getting a PhD, I joined the faculty at the university, and but I wanted to change the way and for the future, and wanted to have the new body for the robotics research. As you know that children love whole body, robot-like robot on TV programs. And also the students entering to our lab want building their own new body robots. So I had to build a special idea and tools to build new robot bodies for them. So I struggled and I found one idea. I wanted to make any toys, radio control toys, as a robot from the computer. Feedback, visual feedback control to the remote body toys. So that then you can see that these robot small body could be toys for children. So I wanted to build an environment to keep development, not only the robot, but also the environment for the robot. We want to call that environment as a mother environment. So we wanted to study about the environment, how to develop the real robot body and brain, artificial brains. And I wanted to have that special methodology for scalability for the future development. In this scheme, we can use any computer, supercomputer, network computer, cloud, and something, and embed it also. But the robot body should have same interface to the brain. Then we can build a scalable environment for the research. So I built this kind of environment. We put radio control transmitter to the real-time computer, transputers. Somebody knows that name of the transputer. Here we have about 50 transputers at the processing, parallel processing, and combined special correlation-based tracking vision based on the transputer. Here we just build a radio toy body, which has radio receivers, control receivers on body, which has about 16 servo motors on body, no computer on body. But those robots' body have the same interface to send back all sensor to the computer site and receive the action command to the body. So in this environment, we could build more than 128 motors, 50 Hertz, and 8 video receivers. So we can share the environment for the student. And also, we can build different types of whole body robots, wheel type robot, quadruped, legged robot, and biped, and ape-like robot, and biped with hands, like humanoids. So the students build their own robot in a short weeks, 2 weeks or 3 weeks. They just combine the modules into the simple structure. They bend the metal, aluminum, and build a joint, and combine and build just a simple hardware. Then it has the same receivers. Then the computer can control the body with the same interfaces. So after building this environment, students could enjoy very much. They build their own body every month, and they build tools for the robot, swing or brachiation, horizontal bars, and skaters like this, and yeah, stairs. So that in 3 or 4 years, several students, master course and doctor course students, showed many demonstration behaviors with that. And also that on this system, the whole sensor information is integrated inside the image, so that we can use that image processor as sensors. For example, this image shows that the middle square shows that tactile sensor suits information. We built a special whole body sensor suit, which is made of the electrically conductive fabric and string. So we build a soft suit as a sensor for any robot body. So the image processor can detect the tactile sensing information, also that stereo left image and right image. So with these tools, the student and we could inheritable and shareable mother environment was the next. So that next, we could separate the development processes with concurrency in development of bodies and brains. This is just basic scheme of the remote brain approach. Then people can parallelly, concurrently develop in the hardware and software. And also that the developer of the behavior can share the mother environment and brain examples, and also the body, and build different types of brain-body combination to study for the next abstraction for the brain description. So brain is how to combine perception to action. So the student can learn from different types of the combination perception to action. Planner approach, AI approach, it has the searching, the sensor action operations, and the feedback loop control. It requires attention selection in the loop, and also the parallel structure. It requires motion arbitration to the single body. The subsumption architecture is one of this architecture. So in this system, the real body is inside the control loop, with observed by the simulated mother environment. So we can see that the ongoing body situation through that visual information, visible information. that it allows us to develop the ongoing advanced trials, challenging the behaviors through the visual feedback to not only the computer, but also to ourselves, developers. So on this approach, the basic bottom is the Lisp-based robot programming system, Cosmos. Professor Inoue drew this line. After he came back to MIT AI lab, the Lisp is a special language. It's a prototyping language, and we can extend infinitely. So one graduate student built our own Lisp processors. So that is the current core language in our lab. The name is EUS Lisp. Dr. Matsui, now he's in ICE, he built by his hand the whole Lisp processing language. That language was open source, but last year we could change the license to the BSD, whether anybody can use it as an open source initiative regulation. Okay, with this language, we can model the body, robot body, and also the other environment. So this slide shows that robot models, which we have developed in our lab, the student built these kind of robot, and also we can buy some of these robot models. And also, this is quite new. Yesterday, you saw that walking DLR biped. It's also that described in this environment because DLR, I have to say this, thank you for hosting Dr. Nakanishi. He's an assistant professor of our lab. And he learned many good things and how to design and how to control in 4 months. And he built a small foot which allowed the robot to get shoes to walk adaptively. So anyway, Dr. Nakanishi learned many ideas from this internship. And he built, described that kind of the combination of our mother environment. And also, these are models which we are using for our research. And also, we build a visual processing environment. Once we have the model described, then the task control scheme could be straightforwardly translated into the just motion sequence, because that we do not need to describe the special visual processing, because that the system automatically verifies the motion sequence. That is the most big advantage to the model-based and visual verified approach. So we do not need program for how to use vision for these tasks. So the system automatically verifies the models with this vision while it's moving. Yeah, that is another topic in our environment also. And this is the video cut. For HLP2, we demonstrate for the TV program, which is designed for the president of our university, introduction of the president. So our HLP2 is also using the same Lisp-based programming environment. So the students just change the model of the body, just scale up and change the dimensions. That's all. Then they can test their own favorable all experiment like this. So if the humanoids become life-size, then we can use any tools, any everyday tools for us, so that we do not need building a special swing or something, table, skaters. We just buy the tools for ourselves. Okay, then we can build a testing environment. In this slide, that many students try to build their own research topics for the future, using tools and how to learn, how to use the tools, and how to recognize movable objects like that. So using this fundamental, we can pile up that fundamental environment as a mother environment. Then we can specialize some of that humanoid function for the company wants. So this is some example. We built the IRT Institute Center under the president of the University of Tokyo. Several companies joined. And we wanted to discuss about which direction is closer real application field market, so that these companies chose different approach. Fujitsu wanted to have the visual application, watching, take caring the elderly people, just sitting, not moving, just sitting. It's enough. And also Panasonic wanted to build a home appliance as a robot, so that we put the arm robot in the kitchen and dishwashers. Then a robot tried to pick the dishes into the dishwashers, and after washing, then the robot pick up to the shoulders. And also Toyota wanted to have that cleaning up and tidy up the rooms. So that those demonstrations done by that part of the mother environment to build the core systems. And also that from last year, almost 2 years ago, there are the Willow Garage company that built special environment tools, loss. And we applied that beta PR2 beta program, and we got one PR2, and we try to extend our mother environment to the open source communities to show more quickly to the real application. And also in Japan, we have a national project, open robot technology middleware project. So reusable component type module software will be shared under the project. So our lab, we combine that Lisp-based environment to this ROS and RTM middlewares. Then student can abstract which is the important direction. And they have to solve, they have to think about how we should build the software, total software for the different tasks with abstractions. And yeah, so this is the third topics. For future challenges, I wanted to show some recent topics on the body, brain, and users. So this is the graph of the torque, horizontal is the torque, and the angular rate. You see that the human knee joint has this curve. And H7 or HLP2, it has a power. It's like this, green one. So you see that humanoid, life-size humanoid, cannot play like a human, speed and torques. Here, red line is ordinary human we have. So we have to build the special devices for the motion, creating the motion. So once the student, so smart student and the crazy student, he built the device with a liquid cooling system. Then you see that robot, he built this robot. Originally that leg is developed for the HLP3 leg, but we changed the gears and motors and drivers. We put our own drivers and gears and computer systems. Then we could jump the 25 centimeter and 44 centimeter on the foot height. So with this robot, he did this work with this robot. So you know that adaptive control, the impulsive, the quick motion response requires high torque drive and high speed drivers. If you use a motor driver, not oil pressure, then we have to solve how to control the currency in a short time and how to cooling the total temperature. But after that, it requires us the good controller for the consistent behaviors like walking or the recovery, push recovery, impact recoveries. So this kind of recovery motion requires so fast computation powers, like 4 giga PC and with a simulated instruction set. It generates candidates a good solution for the stepping, the real-time planning, motion planning. It's embedded in this robot. That line is a fiber cable. The PC is outside the body. It's also the remote brain, and we can change the brain site for this experiment. And also we wanted to change the body flexibility with spine, like human, and redundancy for the robustness. So far we have built several prototypes of the musculoskeletal humanoid like this. This is the current Kojiro, the 5th version. It has a non-linear spring antagonistic structure inside the wrist, then it can impact motion like this. But you see, the human can play like this. So we have to build another ideas to reach this way. Okay? And also it requires design challenge and fabrication challenge. These robots, there's no commercial element parts. We have to build by ourselves. Rapid prototyping, powder, laser selective sintering system, and very small special microprocessor. The size is very important. That robot has more than 50 microprocessors to control that whole muscle, wire muscle system, and distributed sensors, and also that special shaped bones. So it requires new way, new methodologies. And also that brain challenges. On the musculoskeletal robots, Dr. Nakanishi solved that one way. His program tried to recognize its own body configuration structures. It has more than 100 motors, pulling motors, like muscle type motors inside. But there is no pre-programmed models for this body. So that the robot have to find its own configuration by itself while it's moving. So that he built a program which recognizes non-linearity inside the space, many degrees of freedom, more than 100 space. You know that SLAM, locomotion, mobile robot, gets a non-linear featured part in the environment. Then a robot can recognize, localize the position, its own location, situation. So it's the same idea. So we call this body inside SLAM technology. Then a musculoskeletal robot will be solved for the body perception. Yeah, that is the current ongoing challenge. And another brain challenge, you know, that acquiring new knowledge or how to operate the special shape or special tools or social tools. So we have to build continuously how to recognize human motion and how to recognize the goal of the intention of the human. So visual capability we have to build, and also we have to build a special rule to infer the attention control and goals to be presented. And also, yeah, this slide includes that video. Yeah, this is a quite new result, collaborating with TUM Professor Michael Beetz. They are building that web-based semantic knowledge acquisition system. And they also that the PR2 robot. So we collaborate building that PR2 experiment. We just ask some goal, pointable goal, I named. We just getting sandwich, something like that, or find my mug cup. Then a robot knows if the robot has some knowledge, data, sensor data, experience, then a robot try to verify that experience before. And also that it has the building map like this. The geometrical, the horizontal map is acquired by robot itself. But through a difference, we have to tell the robot. And also that we have to tell the robot how to operate the elevator and how to reach, where is that shop which selling the sandwich. So that kind of knowledge is, we have to put the environment. But that Professor Michael Beetz's group have the semantic inference system so that human just send a query, target, or the goal. Then a robot check that knowledge database of the captured from the internet. So that kind of combination is the first trial we could show that we showed the last IROS. Yep. This is also that one way that we have to build. We have to think about how to build a brain which can acquire new data or knowledges. This is the one way we think. And also the challenges for users. Here is the two person. One is Dr. James Kaffner. He was the postdoc of our lab. He was the CME associate professor. And after that, he joined Google for the cloud robotics. He built the Google autonomous cars. He's now building. And also he's now building a special cloud application of the human smartphone application. And also that student of the Dr. James Kaffner, Dr. Rosen Bianco, he's currently now postdoc in our lab. He created the RAVE, which is developed by James, but he completely rewrite the program for the open source. That is Open RAVE. Right now, 300 users are using, and every day we have the mailing list, the query and the answers. Anyway, so he wanted to apply that motion planning software, Open RAVE, for the real application, real industry, to how to assign the many robots in a line. Then our program provides us that geometrically conflict and the time of the sequence conflict. So his program supports that calculation, and he built a venture company, Mujin, and he just started to apply his software for the future. This is, I think, it's very important challenge. And also, I wanted to say, future challenge for users. Let's become users of robots. Every day, we have, in the future, probably we will use robots, but if we do not use the robot every day, we cannot use it in an emergency situation. So, robots should become a must entity. I mean that if you do not need that robot, then the robot do not require to survive. So we have to think about which is a must requirement, must need for myself. So after thinking about that, I wanted to buy or borrow the robot to test for my work. This is a remote professor. Here is a Vigo, and this is Anybot. This is in my room. Here is a browser to communicate. These robots are developed for the telepresence, but they do not have the map by itself. So after testing in 1 hour or 2 hours, I wanted to change that brain. So the robot have to have the function to catching the environment information by itself. So current situation is like that level, so that for the future, we have to move the next stage. This is the conclusion. We have many things to do anyway for the future. Body, brain users. Brain is a very hard part, but users requires the simple interface for just pointing. Acquired goal function. Acquired means that brain should acquire by itself. So important thing is keeping shareable common foundation and the extendable platform, hardware and software, and also everyday use to allow to use it in emergent situation, and become users of robots, using robots for your own jobs and everyday life. Keep inheritable development with challenges, and inherited development requires strong power to make it simple through abstraction. And also, I like to appreciate the encouragement I received from Professor Hiltzinger while we have kept on this direction is a very important key factor for the next. Thank you very much.